All right, we are jumping into 10.3. Remember, all of chapter 10 is just about two-dimensional figures. And the reason why we're doing that is because next chapter is three-dimensional figures, and you can't do that until you know area. So what we are doing today is we are going to do area of regular polygons. We have already talked about the area of a rectangle, of a parallelogram, of a triangle, of a trapezoid, and a rhombus, and a kite. You know all of those formulas. And what we're going to do now is we're going to be trying to find out the formula for the area of a regular polygon, and we're going to adapt one of these or more than one of these formulas so that we can develop a new formula. Before we can do that, we need to remember what the word regular means. Does anybody remember what the word regular means? There's two aspects to it. What does equilateral mean? Congruent sides. What does equiangular mean? Congruent angles. Okay, unlike a triangle where if the sides are congruent, the angles are congruent. If the angles are congruent, the sides are congruent. For a polygon, that is not always true. So if the sides are congruent and the angles are congruent, we call it a regular figure. Now, if you have a figure that is not regular, let's say that pentagon, we are not developing a formula for this. What you would end up having to do is break this up into two different figures. All we're doing today is regular polygons. So this is stuff we covered in a previous chapter. I just want to make sure you guys remember that 6 sides is a hexagon, 7 sides is a hepta or septagon, 8 sides is octagon. Then you had nonagon and decagon. The only other one that I was wanting you guys to memorize was dodecagon, and everything after that, let's say 15, I'm sure there's a name for a 15-sided figure, but we're just going to call it a 15-gon or a 27-gon. Questions? Before we can jump into this, we need to know the anatomy of a regular polygon. Obviously, this point right here is just the center. Now, the reason I put a circle around this is if you have a line segment going from the center to one of the vertices, not to the side, but to a vertice, looking at this circle, what would we call that if that was a circle? The radius. We still call it a radius. So if you go to one of the vertices, it's a radius. If you go to one of the sides at a right angle, that is something new, and that is an apothem. It sounds like my son, who has a hard time pronouncing things, saying a possum. Okay, so I saw a possum, Dad, at the zoo. Okay, possum. Anybody have any questions about the difference between a radius and an apothem? Apothem goes down to the side at a 90-degree angle, and a radius goes to a vertex. No questions? Okay, it's good for us to know what the actual angles are inside of these. So let's say I wanted to know this angle right here. Using some logical reasoning, does anybody have any ideas about how we could find that angle? Yes. Good. So you can do 360 divided by the number of sides, in this case 5, and that will give you the whole entire angle. So that gives you, measure Aldebaran calculator, that gives you 72 degrees. Now, we've worked with triangles a lot in this class. What is the most famous triangle that we work with? The one that has a bunch of different tools that always work with it. Yeah, we've got base angle theorem for isosceles triangles, and this is an isosceles triangle, so we can use that. But there is a different triangle where we have many different things we can do with it. Not equilateral, a right triangle. So somehow I want to find a right triangle inside this. And it just so happens that you'll have your full angle, and when you drop down an apothem, since it intersects at a right angle, you make yourself a right triangle. So that is the next question they ask. What the heck is that angle? Because that would be super helpful for us to know when we're doing like calc and stuff like that. Well, if the whole entire angle for that problem was 72, then what is this angle right here? 36. Great job. Measure of angle 2 is going to be 36 degrees. And we are now at the point where we have a 90-degree angle, a 36-degree angle, and they just want you to figure out what that one is. What is that angle going to be, and how would we find it? That's 36. We know the apothem drops down at a right angle. So how do we find out what's left over? Yeah, 180 is inside of a full triangle. So we could do 180 minus the 90 from the apothem dropping down minus the 36. And someone with a calculator, what does that give us? You're definitely going to need a calculator for today's lesson. (180 minus 90 minus 36). 54 degrees. Does anybody have any questions on that? What I want you guys to do is see if you actually know what you're doing. This is measure of angle 1, measure of angle 2, and measure of angle 3. Now, this is different, though. This is now we have 4 sides, and that's half of it, so it's going to be an octagon. Find out what the whole angle is for an octagon. Find out what it is once you have the apothem bisecting the angle, and find out what's left over. People at home, I'm going to pause this video so you can give it a shot as well. All right, so once again, the reason why it's 360 is because all of the angles come together to make a circle. So over here, all these would come together to be a circle as well. 360 divided by the 8 is going to give me 45 degrees for the whole angle. When the apothem comes down and cuts that angle in half, it becomes 22.5. Questions? And then lastly, the triangle has 180 degrees. You take away the 90, which is made by the apothem. You take away the 22.5, which is the angle for angle number 2. And what does that give you? 167.5? No? 67.5. Does anybody have any questions on this? Okay, just a friendly reminder. If you have a rectangle, that is going to be base times height. If you have a parallelogram, that's base times height. If you have a triangle, that's 1/2 base times height. If you have a trapezoid, that's 1/2 base 1 plus base 2 times height. If you have a kite or a rhombus, that is going to be 1/2 diagonal 1, diagonal 2. Am I forgetting any here? Now, okay, so what you guys are doing is I am giving you, people at home, this is what the kiddos have. They have a pentagon like this, and I've labeled all the sides. I first labeled the apothem, and I called it A, so I couldn't use A again. So I labeled that side as B, C, D, E, and F, and they all have little triangles in there like this. And what the students are going to do, you also have that for a hexagon, because I wanted to have one that was even and one that was odd. Let me just pull it up on the board and show you what the kiddos have. This is what the kids have right here. So what you guys are going to do is cut out each one of the triangles, making sure to leave on the letter that's over here. So cut out, in this case, 5 different triangles and start playing with them and see if you can get yourself a square, a parallelogram, a trapezoid, or any of those things. Once you figure out what you get, then try to adapt the formula. You will get one type of figure for the 6-sider, and you'll get a different figure for the 5-sider. If I was you, I would go with the 5-sider first to develop the formula and then confirm it with the 6-sider. It's going to be easier to develop the formula with the 5-side one. So people at home, I'm going to pause the video so the students can do this activity to develop the formula. You're trying to change these regular polygons into a shape you've already worked with. Great. All right, kiddos at home, here is basically what happened. I had the students work with the pentagon first. So here is your pentagon. They put the triangle like that. That's the second one, the third one, the fourth one, and the 5th one. They had the B, the C, the D, the E, and the F in those locations with a height of A. So when we look at this, this is what type of figure? A trapezoid. So that's 1/2 base 1 plus base 2 times height. I just have to fill in with the specifics for our figure. So that would give us 1/2. Base 1 is going to be B plus C plus D. Base 2 is E and F. And the height, what is the height of our figure called? A. And what is a different way I can say all of the sides added up, which is basically what this is saying? What is a different name for all the sides added up? What is it? No, like when you add up all the sides of a figure, we call that perimeter. So I could say, forget all that, let's just write perimeter. And there you go. The formula is 1/2 apothem times perimeter. When the kiddos had 6 of the triangles, it was 1, 2, 3, 4, 5, and 6. You guys with me?
Yeah.
B, C, D, E, F, G. What is the figure you got when you did a 6-sider? A parallelogram. That's base times height. What is the base of this thing? How much of the perimeter is down below? What is B plus C plus D? How much of the perimeter are those sides? Half. So half of the perimeter is represented by the base down here. The height is still apothem. Do we get the same exact formula? 1/2 apothem times perimeter?
Yeah.
Yes, we do. So when we had 5 sides, an odd number or an even number, we got 1/2 apothem times perimeter. This is only one method of trying to develop this formula. There's many different ways to do it. So let's go ahead and put this into action. Oh, I want to tell you exactly what you're going to mess up on. You are going to accidentally say 1/2 apothem times side length. Not side length, it's supposed to be perimeter. So on this figure right here, we would say 1/2, the apothem is 12.3, and the perimeter is not 8. That's only one of the sides. I'll count for you. That's 10 sides. What is the perimeter going to be then? 80. And someone with a calculator, I need you to put 0.5 times 12.3 times 80 and tell me what you get.
$984.
984 inches squared. Does anybody have any questions when they go over and give you the apothem and they give you a side?
Yeah, you're supposed to
Divide by 2. Okay, so that's not it. What is it? 492? Okay, there we go. Any questions? All right. I can do another one. Does anybody, this is if they give you an apothem of 8 and they gave you a side length of 11.6. Does anybody need me to do another problem where they give me everything, where you don't have to solve for anything? Questions on this? I assume all phones are away? Great, thanks. Okay, now, there are 2 stars of this show. The first one, or the one that we're going to use most, is a hexagon. We learned up here that the central angle, the angle inside here, can be pretty much anything. When you are dealing with these figures, you end up with a special set of angles that are really helpful for us. Let's think about this. What is this whole entire angle going to be? If it's 360 for all of them and it's a hexagon, so it's 6 sides, what do you get for that angle? What's 360 divided by 6? 60. Okay, so this whole entire angle is going to be 60. And when you drop down your apothem and cut that angle in half, what does this become in there? 30. Do you see how we have a 30, 60, 90 inside of a hexagon? It is standing upright with the bottom being the shortest side. Does anybody have any questions? You got that 30, 60, 90 that's like that. So you're going to have a bunch of hexagon problems. The next one, if we have a triangle, what is that whole entire angle going to be? You got 360, there's 3 angles, so it comes out to be how many degrees? 360 divided by 3 gives me 120. Now, when you drop down your apothem, though, how many degrees is that inside there? This is going to be 60, 30, and 90. So both of these have 30, 60, 90s. A pentagon doesn't, an octagon doesn't, a decagon doesn't. These are the only ones that have the 30, 60, 90. And then this, now you got to remember, whenever you have a square, you can do base times height. It's also a rhombus, so you can do 1/2 diagonal, 1 diagonal, 2. Or you can do 1/2 apothem times perimeter because a square is a regular polygon. Use any one of those, being as lazy and efficient as you can. If you end up doing 1/2 apothem times perimeter, let me show you how you have a 45, 45, 90. This is going to be 90 degrees right here. because it's 360 divided by 4. And when you drop down the apothem, then you end up with a 45, 45, 90 triangle. That is a 45, 45, 90, and this one is also a 45, 45, 90. And oddly, this is also a 45, 45, 90. So these are embedded in squares all over the place. But you guys should be lazy and efficient. If you can do it in a different way without radicals and it's way easier, then do it in that way. I'm not going to force you to do it like with apothem and perimeter where you have to deal with radicals. Does anybody have any questions? So let's do a few problems. On this one right here, it's a regular polygon. We know it's 1/2 apothem times perimeter. What do we have enough information to find, the apothem or the perimeter? Perimeter. So 1/2 apothem times, it's 6 sides, and each one is 16. I'll do the math for you. That's 96. Now you have to find out how you use 30, 60, 90s to find out the other information. Here we go. If this whole side is 16, then what is this right here? 8. And now we need to find the apothem. If that bottom is 8, the apothem is what? How do you go from here to here on a, not by 2, nope, by rad 3. You guys absolutely 100% need to memorize the 30, 60, 90, and 45, 45, 90. It will bite you in the hiney if you don't. So now we have 1/2 apothem, which is 4 rad 3, and times 96. Half of 4 is 2. 16 times 6 was 96, right? 16 times... What did I... Yeah, it was 8 rad... Oh, there we go, there we go. Thanks. Yep, that was the problem. I was wondering, because this didn't seem like it made sense. That was 8 rad 3, which pushes this to be 4 rad 3. I was realizing the answer was not matching up with what I've gotten in previous periods. Okay, so now we have 4 times 96. Did you guys get 384 rad 3 centimeters squared? A little recap. If you didn't memorize your 30, 60, 90s, you bombed the quiz from whatever chapter that was. Then you bombed the test. Now you're not going to be able to do this quiz, nor will you be able to do this test, nor will you be able to do next quiz for next chapter because that has 30, 60, 90s, or the next test, or Algebra 2. 30, 60, 90s are all over the place. Take a second to memorize how to get around a 30, 60, 90. Questions? Okay, let's look at the next one. 1/2 apothem times perimeter. With the information they gave us, does that give us the apothem or the perimeter, both or none? Is that an apothem though, or is that a radius? It's a radius. So we have nothing. At this point, we have to drop down an apothem, and we have to solve for all the stuff. Let's jump around our figure. If this is 10, it's a 30, 60, 90. Remember, this works because it's a hexagon. If it was an octagon, it would not have a 30, 60, 90, but it is. That's your 30, that's your 60 and 90. If this is 10, how do we get here? 5, and then how do we get to here? Rad 3, 5 rad 3. Now we have everything we need. Half of the side is 5, because that's what we just solved for, so it's the whole entire side. 10. Now we have everything we need. 1/2 apothem, which is 5 rad 3. And the perimeter is 60, because it's 6 of those 10s. Half of 60 is 30, and 30 times 5 rad 3 is 150 rad 3 inches squared. Does anybody have any questions about how you use 30, 60, 90s in a hexagon? Often, the next section that we do, I believe, we end up doing where you have to use trig, and people just start assuming everything is a 30, 60, 90. It just turns out for a hexagon, it's a 30, 60, 90, but not for an octagon, not for a decagon. All right, I'm teaching you guys to be mathematicians, crazy, lazy, and efficient. Out of the formulas, base times height, 1/2 diagonal 1, diagonal 2, 1/2 apothem times perimeter. Looking at this, what is the laziest and most efficient way to do it? The top one, the middle one, or the bottom one? Which one? Okay, if I do base times height, that means that I have to use, this is a 45, 45, 90. I'm going to have to somehow get here. Okay, does everybody see that we already have half of the diagonal? It's going to be super easy to find the rest of it. Let's use this formula right here, and then I'll do it the different way to show you get the same answer. 1/2 diagonal 1. What is diagonal 1 for this thing? 20. What is the other diagonal? 20. Half of 20 is 10, and 10 times 20 is 200. That is one way to do it. I'm going to show you the other way just to show you that it matches up. If this is a 45, 45, 90, how do we go in this direction? Do you multiply or divide? By what number? Nope, rad 2. And when I do that on the side and simplify, I get 10 rad 2 over 2, which is 5 rad 2. Okay, if this side here is 5 rad 2, what is the whole entire side? 10 of them. Great job. 10 rad 2, not 10 rad 4, 10 rad 2. Let's go ahead. I'm going to do it in two different ways. I'm going to do base times height. 10 rad 2 times 10 rad 2. That gives me 100. Remember, any radical times itself is the number under the radical. So rad 2 times rad 2 is just 2. Do we get the same answer? We do. Let's do it in one other way. 1/2 apothem times perimeter. Oops. 1/2, the apothem in this case is going to be 5 rad 2 as well. And how many rad 2s do we have to go around the whole entire figure? If one of them is 10 rad 2, how many rad 2s to go all the way around? 40 rad 2s. And let's see if we get the same answer. Half of 40 is 20. 5 times 20 is 100. Rad 2 times rad 2 is 2. Do we get 200 again? We do. So what is the easiest method? A, B, or C? A, next easiest, and then C is nightmare. So lazy inefficiency, I'm not going to take off if you're clever and go, oh, I remember that a square is a rhombus, so I'm going to use the diagonal one. That's fine. I got one other problem I want to get through with you guys here before the bell rings. This triangle is going to have, we're going to do 1/2 apothem times perimeter. Make sure you understand that this is not half of the way to the top. Okay? You can't just double 8 and say that's the height. It doesn't work that way. So 1/2, do we have the apothem? Yeah, what is it? 8. And we don't know the perimeter yet. We're going to have to jump around our figure a little bit. Remember, whereas in an octagon, not an octagon, on a hexagon, the triangle is sitting up like this. This one, it's tipped on its side. So if this is 8, how do I get to that side? 30, 60, 90 like that. If this is 8, how do I get over here? Because we developed it. The angle inside is 360. Yeah, you got it? Okay, cool. So what do we multiply to get this one over here? Okay, so that's 8 rad 3 is half of the side. 16 rad 3 is the whole side. And what is going to be the perimeter then? Are you positive 16 times 3 is 48? Yeah? 48 rad 3. So here we can say half of 8 is 4, and 4 times 48 rad 3. What does that give me? 192 maybe? 196? 190 something? What is 4 times 48? 192 rad 3. Now this class is obviously a bit of a nightmare for you guys if you did not pay attention in Algebra 1, because rads are everywhere. Okay, the main things are, do not assume that there are 30, 60, 90s and everything. If you have like an octagon or a pentagon, you don't end up with a 30, 60, 90. You end up with some other weird angle. But if you do have a hexagon, you can use your 30, 60, 90. You have a 45, 45, 90 on this one, and you have a 30, 60, 90 on this one. All right, cool, that's it.